about chemisorption, we are basically talk about heterogeneous catalysts where you have support and the metal deposited onto those. So metal can be different type, different forms, different size as well. Can somebody mute your mic? Thank you. Fine. So when we develop any catalyst, let's say if I need to develop a 5% platinum on alumina, now if I ask three people to make this, all three people, if given the same ingredient, they will not make the catalyst same. There would be difference. The difference would be in their active metal area, in metal dispersion, in the crystallite size. Then let us consider that we found one which is the best one, and then I need to see that at what temperature it is able to reduce, what temperature it is able to oxidize, and what are the acid sites present, what are the basic sites present. So there are two different type of tests you can perform. One is for the quality check and second is for the efficiency check. Different industries where you can use the Chemisorption. And the difference between Physisorption and Chemisorption is that Physisorption is weak interaction, Chemisorption is strong chemical interaction, it is non-specific, it is specific. Here the activation energy is low in Chemisorption, it is high. Heat of adsorption is low in Chemisorption, it is high. It is, we usually do it at near boiling point, and here we use high temperatures. It is easily reversed, it is difficult to reverse. With an increase in the pressure, the Physisorption increases. Here we typically do not see any impact of increase in pressure as such, but with temperature, if you increase the temperature beyond some point, then the Chemisorption starts to decrease. While in case of Physisorption, you increase the temperature, you will find a decrease in the adsorption capacity. Physisorption can also be a multi-layer process, but Chemisorption will always be a single layer process. Now, as we discussed, the Chemisorption can be of two types. One is static Chemisorption, another one is dynamic Chemisorption. Now, the difference in static and dynamic is in a way, like there are two ways of understanding is, one is that in dynamic things, the gases are flowing continuously. There are no pressure regime generated, no pressures involved, no pressure transducer involved. It is a continuous flow of gas similar to gas chromatography from one end to another and going to the TCD. Another is that in static, you can also take it like that in static, the temperature is kept constant, and in dynamic, the temperature is changing. Now the dynamic is having two different type of reactions. One is temperature programmed reaction and one is pulse chemisorption. So please be clear here that in dynamic, in both the cases of TPRs, TPX and pulse chemisorption, we are using TCD as a detector and the gas is flowing from one end to another in a U-shaped cell. Now, the pulse chemisorption and the static chemisorption are similar in a way in that in both the cases, the temperature is kept constant. While in temperature programmed reaction, the temperature is changing continuously. In static mode of chemisorption, it is very similar to Physisorption that we discussed, but the experiment is done at a higher temperature. A known quantity of gas is introduced into the sample cell, pressure is measured pre and post equilibrium, and it will give us two different type of isotherms as we did there, adsorption and desorption. Here we don't get the adsorption and desorption, here we get combined and weak. In combined, the gas will get absorbed over both the metal and the support, and when we evacuate, it will come off from the support but not from the metal, because over metal it has been chemisorbed, it's not physisorbed. So it's like this, that it is a support, metal ions are gray. When we apply the red gas molecule to it, it adsorbs over the metal as well as over the support. But when we evacuate, only those molecules which are weakly bound over here comes out. So we get two different type of isotherms. One is combined, another one is weak. And when we subtract the weak data point from combined, we get the strong. Now the strong gives us the information of those gas molecules which get adsorbed over the metal atoms. Talking to the TPX mode of chemisorption, where the temperature is continuously increased in a linear ramp. Here we typically use an inert gas as carrier gas and the adsorptive gas, the reactant one, as we do over the gas chromatography. One inert gas and one reactive gas. Since the temperature is continuously changing, we call these temperature programmed reactions. They can be different type of reactions, can be temperature programmed desorption, temperature programmed reduction, temperature programmed oxidation as well. Temperature programmed desorption, let's understand in a way that when I say desorption, first it should have something adsorbed onto it, because if until it has something adsorbed, it cannot dissolve. So in TPD, we basically adsorb some gases onto the material first, either ammonia or CO2. So we saturate the sample with ammonia first, ammonia bind everywhere where it can. Once it is already there, then we apply heat and flow an inert gas onto it. Along with the inert gas, since as you keep on increasing the temperature, the adsorbed ammonia starts to dissolve. And this is why we call it as temperature programmed desorption. So just consider this way that if it is a support, some metal present over there in different forms, ammonia adsorbed all over. And as we keep on increasing the temperature, at one temperature, one type of site released, another temperature, another type of site released ammonia, and the third temperature, another type of site released ammonia. So we get three different type of peaks. Now, since ammonia is a basic gas, it gives me the information of acidic sites. So it tells me information. There are some weak acidic sites which releases at lower temperature, and there are some strong acidic sites which releases ammonia at high temperature. And this is how you understand the weak and strong acidic site present over the catalyst and the total acid site concentration. Instead of ammonia, had it been CO2, the CO2 is used for basic site concentration because CO2 is an acidic gas. So if you have done this experiment with CO2, CO2 would have bound over the acidic, the basic sites only. So you will get the basic site information with this. Now coming to the temperature programmed reduction, as the name say, we need to reduce something. We are using such gases also. So we either can go with carbon monoxide or you can go with hydrogen. Let's consider hydrogen, it's much safer. So when we want to do this, hydrogen is typically mixed with nitrogen or argon, not with helium, because the thermal conductivity of helium and hydrogen is very same and the TCD won't be able to detect it. So we mix the hydrogen with either nitrogen or argon. We flow this mixture over the sample, and if there are something which can get reduced, the hydrogen will be consumed. And this change in the hydrogen concentration will be detected over the TCD and it will give you peak. So you will get a signal like this, and we also find to know that where the peak is coming. Now this peak will give us the information of ease of reduction, how easily it can reduce or how hard it can reduce. So if the temperature is lower, it is easily reduced. If the temperature is higher, it is hard to reduce. Similar to TPR, the TPO is performed. In this case, the oxygen is mixed with helium and we flow the mixed oxygen to the sample, and we see that how the oxygen is getting consumed. The change in the oxygen concentration in the mixture is being detected by the TCD, and you get to know the ease of oxidation. Just giving an example of carbon material. On oxidation, it gives us three different type of peak, which gives us an idea that there are amorphous carbon, filamentous carbon, and the graphitic carbon present in the material. The graphitic get oxidized at a higher temperature. The amorphous get oxidized at earlier temperature, lesser temperature. Then you can also perform the pulse titration, as we discussed that at the pulse titration, the temperature is kept constant, similar to the static one. Here we injected some amount of gas molecules or gas volume to the sample. Let's say we injected this injection, 100 cc injection, and some of the gas molecule adsorbed, some remain unadsorbed. Whatever remain unadsorbed is going to the detector. Second injection, some again adsorb, whatever remain adsorb going to the detector, but this amount is slightly higher than this one. So I am getting a slightly bigger peak. Third injection, I now my all the sites are already filled. Whatever I injected went directly to the detector, even a bigger peak. The fourth, fifth, sixth subsequent injection would be the same way. When I started getting a similar type of peaks, it gives me an information that my sample is saturated now. It's not taking anymore. And I back calculated how much in each injection the sample has absorbed the gas. Then it gives me the monolayer uptake capacity, the same information which otherwise I would have got from the strong chemisorption. Strong chemisorption also gives me the detail only that how many number of gas molecules deposited over the metal once I subtract it from combined and weak. So overall, from the chemisorption, you can take the monolayer uptake, you can calculate the active metal surface area, you can calculate the degree of dispersion, you can calculate the crystallite size, you can calculate the heat of adsorption, you can calculate the activation energy. When you say monolayer uptake, it is like how many number of gas molecule basically attaches over the metal. Active metal surface area, for this you need to know the stoichiometry of your gas material. So let's say if I'm talking about hydrogen can settle over like it can go to one atom of metal, or it can go to two different atoms as well, because it has two possibilities to attain over there. Similar to CO, it is going to one or it is going to two molecules. So this stoichiometry information is also required to understand the active metal surface area onto it. Then the metal dispersion. If we are developing catalyst and we have some lumps over there, when there are lumps, all those metal atoms which are in the core will not be accessible to the gas molecule, and your dispersion would be less. A good dispersion sample where everything is properly spread, no lumps are there, or even if the lumps are there, the lump size is very small. So the metal dispersion describes the ratio of the number of active metal atom available for the reaction to the total number of metal that we deposited over there. Average crystallite size. The crystallite size is the size of that lump. The lower the crystallite size, the better the dispersion would be. And you can also calculate the heat of adsorption over your machine. This is another feature of chemisorption, which you can only perform with this machine, because you can also perform a physisorption onto it. Now, heat of adsorption is calculated using the Clausius-Clapeyron equation. Now, Clausius-Clapeyron equation requires pressure and temperature readings. Now, had it been a dedicated chemisorption unit, you will not be having the pressure readings over there. They don't have the pressure transducers. But since you are having a hybrid unit which can perform both the chemisorption and physisorption, you can get the pressure readings also, so which can help you in determining the heat of adsorption. Now, heat of adsorption can be of two types. You can calculate differential heat of adsorption. You can calculate the integral heat of adsorption as well. Then you can also calculate the activation energy. For activation energy, you need to perform any sort of temperature program reaction where you have to have three or at least three different type of same study, but the heating ramp should be different. So if I have done the TPR from 50 degree to 900 degree, at one go, I would do it at 10 degrees centigrade per minute ramp, then another at 20, then another at 30. When I do that way, I get these type of graphs at 1, 2, and 3, and this gives us a plot of Arrhenius plot, and this Arrhenius plot gives me the activation energy calculation. When you talk about any chemisorption instrument, ideally it should have all those things that you are already having: static chemisorption, then the dynamic chemisorption, in dynamic the pulse and the TPR as well. These are the requirement for this: the flow sample cell, temperature furnace, protective feature, cooling air felt, sample temperature thermocouple, TCD, calibration port, if required, the mass spectrometer, and if you are dealing with mass spectrometer, a turbo pump. Cool trap, customizable chemisorption macro, automatic switching between the gases, powerful peak analysis software, and multiple data reduction designs. Now let me take it one by one. So the Autosop IQC that you already is having both the both the things. You have the Physisorption capacity, you also have the Chemisorption capacity, and if ever you want to add the capability of mass spectrometer, it can also be added to it. It's an optional thing, so right now it is not with your system, but it can be added anytime. The furnace that you are having is having dual thermocouple for independent temperature control and over temperature production, and also we have automatically positioning furnace rate. The cooling air facility here in this case for Chemisorption is within the machine itself. So at the base of it, where you keep the deva, there is a flap, and if you remove this flap, you will find that there is a vent holes over there, and these vent holes are basically for cooling the sample. We already have an inbuilt air cooling facility. So we have a fan over there which will cool your sample. So rapid furnace cooling without utility air. So you need not to have a compressor. It's already there. It will cool down your furnace very fast. And the rate of cooling is in a way that from 600 to 40 degrees centigrade, it gets stabilized within the 30 minutes. Then the intelligent software that you have with you, ASIQ-Win is the same software which you can use to perform the Chemisorption as well. You can assign different gas inputs to different gases for Chemisorption or Physisorption, whatever you want to perform. Chemisorption treatment macro. In the macro, you can tell that what exactly you want to perform. Say if I want to change the temperature to X temperature with this ramp, you can set the same over the software. For the pulse titration, as I said, that we injected. Now, for doing this, it can be done manually with a syringe, or it can be done automatic with the calibration loop as well. And this is macro TPD result. Now, whatever peaks you have obtained with the Chemisorption, you have to have a software feature where you can deconvolute your peak, because it's quite possible that one big peak may contain 3 smaller peaks inside, and which are not visible by our naked eye. So we need to deconvolute these peaks to understand how many peak it is containing. I'll just show you a video which will give you a better idea what exactly I mean here. I'm just opening one file. This is an ammonia TPD file. This is the graph that is coming. If we see such, it seems like we are having 2 peaks over there. Let us open it in another window, which is known as QC fit. We are 2 peaks over there. Now, this QC fit will allow us to do different features. So first we did that whatever is coming below this line, we removed the baseline. Then we selected different type of peaks. There are different type of peaks. So whatever you want to select, we selected Gaussian first, and then we add the peaks. To add the peaks, you just need to click over this plus and it will automatically add. Now you can add another. And if you find there is still a possibility to add another, because this yellow line, you need to see that it is properly fitting there or not. Until unless it is getting fitted, it is not a good fit. Now we see that it is properly fitted, and also on the lower part of it you will see these zigzags. These zigzags are basically the residuals, and they should be as low as possible, and when they are very low, it means you have properly fitted your sample. Now, since initially they were looking like 2 peaks, but when we deconvolute it, it gives us an idea that there can be 4 different peaks. So this is what I meant with the deconvolution of it. So this is the software window when we do the static Chemisorption. Similar to the Physisorption, you have different pressure points, incubation time, tolerance, and what you want to do over here. Combine 10 points, combine 20 points, combine 40 points, then the weak 10, 20, 40 points like this. So we do the combined and we do the weak. Strong is calculated. Thank you, Ji. So this is all about Chemisorption from my end. And if you have any query regarding Chemisorption, please come up.
Sir, may I ask the questions regarding the points that we have discussed?
Yes, sir, please.
Yeah, so in that case, you have told us that we have to start the points from 10 to the power minus 5. So if we want to save the liquid nitrogen or time, so can we start for a material which surface area is around 1 to 150 and it's a mesoporous. So can we
Okay.
shift the starting points from after like 10
So
to the power
if you
minus
already
50 or
know that it is a mesoporous, you